Hello. The aim of our experiment is to design, implement, and analyze kernel space monitoring module that observes and records the behavior of Linux Completely Fair Scheduler, or CFS. The experiment demonstrates how CFS distributes CPU among runnable tasks, how virtual runtime influences scheduling, and how scheduler behavior changes across CPU bound, IO bound, and mixed workloads. We start by installing Ubuntu on a virtual machine using VirtualBox. Here is the official website where you can download the installer for your OS. Next, download the Ubuntu ARM64 server ISO from the Ubuntu website using this link. Since I've already downloaded both the files, let's jump to creating the virtual machine itself. To create a new virtual machine, start by clicking on New. Name your virtual machine. I'll name mine Ubuntu. Select an ISO image. Give it a username and a password. I am allocating 4 GB RAM and 2 processors and keeping the hard disk as it is, and selecting finish should start your virtual machine. Now this process will take a while. Now I will enter my login and my password. Now that our OS has finally been installed, let's run sudo apt update. We run sudo apt upgrade -y. Sudo apt install task cell sudo apt install Ubuntu desktop. This should enable a full graphical desktop. It took about an hour for this installation to get completed. After the installation is completed, we write sudo reboot now. So now we log in using our password, and we are done installing the virtual machine and our virtual OS.
So the objective was to understand how the Linux kernel manages CPU scheduling in real time by building a custom kernel module that monitors scheduler behavior from inside the kernel itself. The module tracks context switches, measures process execution times, and exposes this data to /proc file system. Let's see how it works. First, let's see what we have here. So we're already in the project directory. Let's see the compiled kernel module. Yep, there we go. This is our kernel module, 331 KB of compiled code that is already built and loaded. Now let's see the test programs that we have. Here we go. We have 3 workload generators. First is the CPU tester, CPU intensive workload, that is compute heavy. Then we test IO, which is file operations with intensive workload, and mix test, which is again combined workload of both CPU and IO operations. These will help us see how the scheduler handles different process behaviors. Now let's load the module and its baseline into the Linux kernel. So first let's load the module into the kernel. We put in sudo in smod scheduler monitor. We enter a password. Now it would be loaded once we check the follow. Here we go. Yes, there it is. The module is now running inside the Linux kernel. Now let's check the kernel messages. Yeah, there we go. We can see that the module has been loaded successfully. The statistics are available at processed of scheduler's stats. And let's look at the baseline, what the system looks like when it is ideal. Yep. So as we can see here, there are total context switches about 488. There are multiple context switches occurring at the same time. Mostly, if you would like to see, 83 context switches which are voluntary. This is our baseline. Okay. Now we run the CPU intensive workload. There we go. We are seeing the results of the CPU bound test, starting with 4 threads for 10 seconds. Yep. This creates 4 threads along intensive mathematical calculations. The scheduler must decide when to switch between them. So let's see the statistics. There we go. You can see it has been actively running, and let's wait for its completion. Now let's see the output that happens when we check the final statistics of this. Yep. So let's look at the results. There are total context switches 8,542. Involuntary context switches are 8422, and voluntary context switches are only 120. The runtime total being 28,500 milliseconds. Why such high involuntary switches? Because CPU bound processes use their full-time quantum. The scheduler has to forcefully preempt them to maintain fairness. That's involuntary switching. Now contrast that with IO bound workload. We can see here the IO bound test for 10 seconds is running. We can use this to monitor our schedule behavior. Total context switches 4,274, voluntary context switches 4,339, and involuntary context switches only 86, which is 2% of the entire total number of context switches. The runtime was only 8,566 milliseconds, which is much slower than the CPU test. Why? Because IO processes spend most of their time waiting for disk operations. They voluntarily yield the CPU while blocked on IO. That's cooperative scheduling. They use much less actual CPU time. So let's go over the results and see what we have actually witnessed. From our previous tests, we have witnessed that in CPU bound processes, scheduler must force fairness, high number of involuntary switches, long time slices, and high CPU usage. And also there is continuous computation until preempted. In IO bound processes self-regulate by yielding during input-output. There are shorter time slices, low actual CPU usage because there is a lot of waiting, and they get priority when waking up for better responsiveness. The Linux CFS, or the completely fair scheduler, adapts to workload type, automatically maintaining fairness while optimizing for different behaviors. The context switching overhead is real and therefore measurable. This validates what we learned in theory. Different workload types require different scheduling strategies, and the Linux kernel handles this intelligently. Now let's clean up by unloading the module. There we go, the module has been unloaded successfully. Therefore, in summary, we built a kernel module, monitored the scheduler from inside the operating system, and verified concepts with empirical data. This project demonstrates kernel programming skills using C and kernel APIs, deep understanding of OS internals and scheduler mechanisms, and real-world validation of scheduling theory. Thank you.